Yeah, so Hess's law is going to allow us to figure out how much heat a reaction gives off without actually doing the reaction. Okay? And the reason why it works is because enthalpy, heat, remember enthalpy is heat content? What the heat content is a state function. And state function means it doesn't matter how you got there. Okay? That if I talk about how far it is to drive to Vegas, it depends on which road you take. You can take the 15 all the way there, or you can get off on the 40, make a left in Laughlin, drive up the river and get there. There's more than one way to get to Vegas. All of those have different miles driven. But if I ask how far away you are when you're in Vegas, it doesn't matter how you got there. The distance that you are from where you started doesn't matter how you got there. So the distance you're away, that's a state function. The distance you traveled is not. The difference between a state function, it just matters where you're at. So that means I can take any path I want as long as I end up at the right spot. Okay? So I don't have to do everything in one reaction. I can do it in several reactions, measure the heats one piece at a time, and use those to figure out how much heat this overall reaction is going to give me. So I can use the heats from individual reactions to figure out the heat for the overall reaction. There's only one thing we have to talk about. We add it up. Sometimes we won't have exactly what we want added up. We'll have to change it a little bit. Sometimes we have to turn it around. That what the reaction I have is for making it as a product, and I want it as a reactant. And if I turn it around, the heat has to have the opposite sign. It takes 40.6 kilojoules to melt a mole of ice. When that mole of ice forms, I get 40.6 kilojoules out. Same amount of energy, different directions. So I turn an equation around. What used to be uphill is now downhill. Okay. Sometimes you don't want to make the same moles of product as the equation has. So if the equation is multiplied, so is the delta H. So if I make 2 moles of stuff, I'm going to get twice as much heat. Make half a mole of stuff, I'm going to get half as much heat. So this reaction, nitrogen and oxygen, makes nitrogen dioxide. That is the equation for how smog forms. Okay. And overall, it's got a delta H of 68 kilojoules. Actually, it's positive 68, right? I'm going up. So delta H for this would be positive 68 kilojoules. Or I'd write the 68 kilojoules over here as a reactant, right? One of those two. But because it's uphill. Now, to figure out how much energy that gives me, I can actually pretend that it happens in 2 steps. First, one of the oxygens hangs on to N, and then the other oxygen. So my first reaction is N2 plus 2O2. Actually, N2 plus O2 goes to 2NO. And I know delta H for that E is 100 and then I've got a second equation where the two NOs react with an O2 to make two NO2s. If I add up these two reactions, the N2, I got plus O2 and then I got plus another O2, so that's plus two O2s. I got two NOs, but I made those two NOs, then I used them right away, so they cancel out. I'm left with on the other side is two NO2s. I can add up equations so they come up with this, that they come up with the same product. First I made NO, then I use that NO. And you're not going to be asked to predict those, but you're going to have to be able to use them. Okay? And what's delta H going to be like for this? Well, this delta H is 180 kilojoules. This one is negative 112. You can't see it, but it says negative 112 right there. So 180 plus negative 112 equals 68. That if I can add up the equations, I can add up the heats, and I'll get the same answer. That's what Hess's law says. If I can add up the equations, I add up the heats, I can get the same answer. I just got to remember, if I turn it around, I change the sign. And if I multiply through by a number, I got to multiply the heat by that number. Okay? So that means we need to compare enthalpies, but enthalpy depends on what room you're in. So they picked standard enthalpy, just said, we're going to pick the room we work in. And we've done this before with STP, where they had standard temperature and pressure. This standard was made by a different group of people. They did not want to work in a 0 degrees Celsius room. So they decided, I'm going to make it a comfortable room, so I'm going to say it's 25 degrees Celsius, which is more like what a lab's going to be. You don't have to work hard to make the room like that. Most rooms are going to be close to 1 atmosphere, close to 25 degrees Celsius. The fact that somebody picked what they were going to compare is why it's a standard. And when they pick a 0. So to say it's the standard enthalpy change, we put a little degree sign. That little degree sign is describing the room for us. It's warmer than the STP room. So this is Hess's law. All you do is make the equations look like the answers. So you're going to pick which equation to use because it has the right chemical in it. You're going to pick whether to turn it around depending on which side you need that chemical. And you're going to pick to multiply it depending on how many coefficients are in your reaction. If you get and the thing is, if you get the parts you want, the parts you don't want will all cancel out. So in setting it up so you get the parts you want, you'll find out that you cancel out the parts you don't want. Just like the NOs canceled on the last example. The overall equation never talked about NO, but it showed up as I added, but they disappeared they canceled out before I got to my final answer. So one kind of problem you'll see on tonight's homework is they'll give you some equations and ask you for the energy for a different equation. So there's 3 equations. Now you might be a little put off by that fraction in the middle. We never write fractions as coefficients. Okay? Why is it there? Because if you look up the definition, it's going to be the definition for burning 1 mole of C2H2. If you balance that equation, it's got a 2 in front of C2H2. It balances 2542. But the definition where I got the number from said for 1 mole. So in order to make it 1 mole, I had to divide the whole equation by 2. And when I divide up 5 by 2, I get 5 halves. Same thing for the H2 down here. I balance this, it's 2H2 plus O2 makes 2H2O, but I only want to make 1 mole, not 2 moles. So I divide by 2, and that's where I get that half. Okay. But I want to take these 3 equations and make this equation. So I have to take the top equations and make them look like the bottom equation by adding. Okay. It sounds hard. It's not. Here's the complicated part. I want C as a reactant. Where is C in all these equations? Why, it's the middle one, right? Okay, so I want the middle equation. C plus half O2 makes CO2. Except I don't want 1 C, I want 2 C's. Right? So that means I got to double everything. So that's 2 C's and 1 O2 makes 2 CO2s. And the delta H for that is the negative 394. But I'm going to have to multiply that by 2 because I multiplied the equation by 2. Because this gives me 394. This is doing it twice, so I'm going to get twice as much heat. The next thing on my equation is H2. Where does H2 show up on here? It's the third equation. And it's H2 plus half O2 makes H2O. Except I want just 1 H2. So I don't have to do anything to this equation. So the delta H for this is going to be negative 286 kilojoules. Okay. So I've taken care of the reactant side. Now on the product side, I need to say C2H2 over here. Where is C2H2 in this set of equations? It's the top one, but it's on the wrong side. So I'm going to have to flip it around. Okay at that? So if I flip it around, that's C2 plus 5 halves O2. And the other side is going to be 2 CO2s plus H2O. So I'm just copying the stuff from one side to the other. And because I turned that equation around, my delta H for this is going to be the negative 1300. But I'm going to have to change that sign because I turned it around. Look at that. Okay, now I'm going to add up the equations. I've got 2 C's. I got 1 O2 here, right? And I got half an O2 here. Oh yeah, it's supposed to be 2 O2s there. That's what. Be 2 O2s. I copied badly. I saw the half and multiplied that. Okay. I was going to run into a problem here. Okay, 2 O2s plus half an O2 is 4 halves plus 1 half, which is 5 halves. Right? So over here I've got 5 halves in front of my oxygen. Over here I got 5 halves in front of my oxygen. They go away. If I used 5 halves and made 5 halves, I'm right where I started. Look at that? That's what I meant by the parts you don't want will cancel out. Okay? I got 2 CO2s here. But I got 2 CO2s over there too, don't I? Cancel out. Got an H2 here, H2O here. I got an H2O over there. They cancel out. And all I'm left with is 2 C's plus H2 makes C2H2. And it's going to work every time because I made it work. I picked what I was going to write. Okay? And because I can do this, that's what I do here. I just add those numbers. So the delta H for this is going to be 2 times negative 394 kilojoules plus negative 286 kilojoules plus, well, minus a negative 1300. Oh, plus, sorry, plus minus a negative 1300, which is, right? Okay. And so I just push those buttons. I add up the equations, means I can add up the heat. So that is 2 times negative 394 plus negative 286 plus 1300 equals 226 kilojoules. Yeah. Okay, so the first one I copied the negative over, and because I left it on that side, it stays negative. Okay, this one was negative, but I turned it around, so I put the negative in front of it. Does that answer your question? Yeah, so if I change it around, I got to change the sign. Tedious? Yeah. Really hard? Nah, just tedious, right? Okay. Okay, for example, this is a reaction we could never do. We could never do this reaction. Because you never find O by itself, and you never find H by itself. Fact is, you never find OH by itself. You don't want to be around any of these things because they are going to kill you. You ever heard the phrase free radicals? They always talk about anti-aging, free radicals. Free radicals means you're an element with a hole that you want to fill, and you're going to go steal somebody's electron to get it. An oxygen by itself really wants more electrons, and it will go get them off of any cell you happen to, any part of any molecule in any cell that happens to be around. So, but I could never do this, but I can do these. I can see how much energy it would take to tear the O's away from each other, how much it would take to break the bond. I can see how much energy it would take to break the hydrogen bond. Okay? And I can make the OH from O2 and H2. So to figure out the equation, the heat for this reaction that I can't do, I need to use these 3 equations that I can do. So the first one, first thing I need is I need O. What equation has O by itself? That would be the middle one, right? And I want O on the other side. So the equation I want is O plus, O forms, so I turn that around, so instead of 2O making O2, I don't want 2 O's, I only want 1, right? So I have to make that 1 O making half an O2. And the delta H for this, I turned it around and I multiplied it by half, right? So that would be the negative 1/2 times the 495 kilojoules. I turned it around to put the O on the other side, and I cut it in half because I only wanted 1 O. So the 1/2 we're cutting it in half, the negative because I turned it around. Okay. The next thing I need is H. I need H over here. And it's going to be just like O. It's going to start off as 2 H's, and I'm not going to want it. I'm only going to want half an H2. And the delta H for that is going to be, I turned it around and cut it in half. And the last thing I want is I want OH on the other side. The only place it shows up in my equation is up top, and it's on the correct side. I just need to cut it in half because I don't want 2 OHs, I want 1, so that's a half O2 and a half H2. And the delta H for that is going to be 1/2 of the 77.9 kilojoules. So when I go to add this up, the half O2s cancel out. The half H2s cancel out. And all I'm left with is O plus H makes OH, which is what I wanted. So I can just add up those numbers. So negative 0.5 times 495 plus negative 0.5 times 435 plus 0.5 times 77.9 equals negative 426 kilojoules. Extra super complicated? So, we did standard enthalpy. Now we're going to talk enthalpy of formation. Formation, form, make, turn into. The enthalpy when you make something. Okay? Because Hess's law is much more useful if you know lots of reactions. The more reactions you know, the more useful it is. In fact, they publish tables of them. So one of the first, once they make a new chemical, one of the first thing they do is figure out what is its heat of formation. The definition of heat of formation: the standard heat of formation is the amount of heat needed to form 1 mole. Should be an M there. To form 1 mole of a compound from its elements in their standard states. Enthalpy is heat. This is often referred to as the heat of formation. The heat of formation is the heat to form it. What are you going to form something out of? You're going to form it out of elements. Standard states means what they would be like at 1 atmosphere and 25 degrees Celsius. And it may not seem like it, but this right here, that defines something as 0. How did that definition, what did it define as 0? What would it not take any energy to make out of its elements? Well, the only thing that would not take any energy to make out of its elements are the elements. How much energy would it take to make iron from its elements? Well, what elements go into iron? Iron. So how much is the heat going to change when I make iron out of iron? Well, you haven't changed anything, so the heat's not going to change. Now, in order to do tonight's homework, you're going to need some of these numbers. You'll need to use table 17.4 on page 530. I want to show that to you. You get a sense of. There's table 17.4. 2 columns. Okay. So if you look, notice that there's some zeros. And everything that's got a 0 next to it is an element. 0, H2, an element. So the diatomics are 0. H would not be 0. Okay. Fe is a 0. Cl2 is a 0. Carbon's got two numbers, but we use a lot more graphite than we use diamonds. So we usually use 0 for carbon. You have to put a little energy into a graphite to make it into a diamond. Bromine's got two numbers because one's a liquid and one's a gas. And at 25 degrees Celsius, bromine's normally a liquid. So at their standard state at 25, bromine's a liquid. To turn it into a gas, I'd have to give it energy. That it takes 30.9 kilojoules to boil that bromine. So if they got two elements, got to decide which one it is. And actually, the more tricky one is down here with water. Okay? Notice they got two numbers for water. One's a liquid, one's a gas. I want to make sure, because it takes, if you make water as a liquid, you'll get some energy. But if you make it as a gas, some of that energy is going to go into boiling the water. So that the vapor is less exothermic than the liquid. Because some of this heat went to boil in that water. I'd say about 44 kilojoules. It takes about 44 kilojoules to boil water. You can see that from right there? Okay. So we need those numbers. They're there. You can look them up. By the way, this is not all the heats of formation out there. It's a really tiny subset. You pick up a chemistry reference book there. Every chemical they talk about, they will give a delta H for. If they can find it, they'll give it to you. They'll give you a heat of formation for it. Okay. Thousands of pages. The ones in my college level book are only 5 or 6 pages long. Small font. Of here's a chemical, here's its heat of formation. Here's a chemical, here's its heat of formation. One right after the other. Okay, so in order to use those heats of formation, we need to be able to write the equation that goes along with them. For example, NO2 is right here, and it says NO2 gas is 33.85 kilojoules. What does that what reaction is that 33.85 talking about? What's the equation that would get you those, where you would have to put in those 33.85 kilojoules for NO2? What reaction would get me that? Well, I know I want to make NO2. What elements go into making NO2? N and O. It's an element. Can N be by itself? No. Can O be by itself? No. There's my reaction. Now I have to balance it. I got two O's on both sides, but the product side only has one N, so I got to put a 2 in front of it. That gives me 4 O's, so I put a 2 there. That's the balanced equation, but it doesn't match the definition. The definition said you have to make 1 mole. My coefficient in front of NO2 is a 2. That would be 2 moles. Right? So I've got the right stuff, I just got too much of it. If I only want to make 1 mole, I have to divide everything by 2, so that would be half an N2 plus an O2. If I just divide by 2, that's what my coefficients would be. And this is the reaction where delta H is 33.85 kilojoules. That's the reaction they're talking about. So when you look up NO2, it's telling you all this. Okay? Because you got to make 1 mole to match the definition. going to meet the definition. The definition says 1 mole. So if you've got a coefficient besides, you should only have one product, and it should have a 1 in front of it. So write the equation for the reaction that would give you the heat of formation of methanol, CH3OH. Well, I know I want to make methanol. So CH3OH has to be on the other side of the equation all by itself. So heat of formation of methanol, I need to form methanol. Okay. What elements go into making methanol? Well, there's carbon. Does carbon get a little too? Carbon's not one of our diatomic. It's number 6, so we don't start till number 7. I'm going to have to add hydrogen. Does hydrogen get a little too? Yeah. And I'm going to have to add oxygen. Does oxygen get a little too? Okay. Now worry about how many. Why won't that 2 right there? I wrote 3 times and then wrote on top of itself. Okay. How many carbons? Well, 1 carbon, so that's okay. How many hydrogens over here? 4. So to have 4 hydrogens, I have to put a 2 in front of H2. And I need 1 oxygen, and I got 2, so I don't want O2, I want half an O2. Half an O2 would give me an O. You don't have to write the whole thing out double and divide. If you can see you only need a half, that's okay. So when I looked up the number for methanol, let's talk about that equation. Extra super tough. So now we can write our own equations. And we've learned how to manipulate the equations. So we've learned 2 things. We can manipulate the equation, we can write our own heats of formation. We can use the heats of formation to figure out the heat of any reaction as long as I know all the heats of formation. Because I can always write a series of equations that'll have all the pieces I need. And the pieces I don't need will always cancel out. So what is the heat of reaction going to be for this reaction? The burning of ethanol. It's going to take us a little while because we have to do all these pieces. We'll have to write my own equations so that I can put them together. Does that make sense? I'm going to write my equations with the heats of formation to get the pieces I need. Because I've got limited board space, up top I will be working on what's going on with the heats of formation, and on the bottom I'll be talking about the whole equation. So I'm using that top as a workspace so you can see why I'm doing what I'm doing. Okay. So the first thing I got is C2H5OH. What would be the equation that got me C2H5OH? Well, what elements go into C2H5OH? Well, C's, H2s, and O2s, right? And it's 2 C's, 3 H2s because there's 6 H's, and half an O2. And when I looked that up in my book, because it doesn't happen to be in yours, the delta H for this is negative 278 kilojoules. So when I look up C2H5OH and I see the negative 278, it's talking about this equation. Do I want to use this equation the way it's written? Well, in this equation, C2H5OH is a reactant. The overall equation is a reactant. So I need to turn this thing around. So in my overall equation, I want C2H5OH making 2 C's plus 3 H2s plus half an O2. And the delta H for that is going to be the negative of a negative 278. I turned it around. So I figure out what equation I want, and then I put it the way I want it. I figure out how to make the chemical, and then put the chemical in the equation on the right side, or on the correct side. The next thing I need in my equation is 3 O2s. So I want to make O2. What elements go into making O2? O. Can O be by itself? No. So what's the heat for that reaction going to be? To make O2 out of O2. So the change in heat for this is going to be 0 kilojoules. And actually, if you look at the table, it's there, and why didn't it show up? If you look at the table, you look up O2, surprise, surprise, it says 0. That makes sense that it's 0, right? Okay. Okay. What about on the other side? The other side of my equation, I need 2 CO2s. So I need CO2 over here. What elements go into CO2? C plus O. Does C get a little 2? Nope. Does O get a little 2? Yeah. Okay. And the delta H for that, I looked it up, is negative 393.5 kilojoules. It's on table 17.4. So down here, where do I want C? I don't want C, I want CO2, and I want CO2 to be a product, right? So I want CO2 over here, and it's C plus O2. But I don't want 1 CO2, I want 2 CO2s. So my delta H for this is going to be 2 times negative 393.5 kilojoules. Right? So we're still doing the stuff we were earlier. First I figure out what the equation is, then I do what I'm supposed to do with it. Okay? And then next thing I need is H2O. What elements go into H2O? H and O. HB by itself? OB by itself? Balance that? Oh, well, 2 H's, 2 H's, 2 O's, 1 O, but I only want to make 1 mole. So this is my, half's on the wrong side. I need a half here to get my 1 mole of O2. And I looked that up, and there's actually a problem. H2O has 2 numbers. So think about this. This is burning ethanol. Are you going to have water liquid or water gas? It makes sense that you're going to get the gas here, right? But what you'll find is on the homework, they tell you which one it is. They put the little symbol after it. So make sure you pick the right one for water. And delta H for that is, we said we're going to do with the gas, that's negative 241.8 kilojoules. Now down here, I want, I forgot my equation. Down when I'm adding it up, I want 3 H2Os, right? I want H2O on the product side, and that's H2 plus half O2. But I don't want 1 of them, I want 3 of them, so that's 3 H2, 3 halves O2, and 3 H2O. And the delta H for this is going to be 3 times negative 241.8 kilojoules. Now I should be able to add these up. I got C2H5 OH. Then I got two C's, but those two C's cancel out. I got two O2s, but I got half O2. So that half O2 is going to cancel out, and to make my life easy, I'm going to cancel out with a half here. So if I take a half away from 3 halves, I'm left with 1. Okay? But that leaves me with 3 O2s. On the other side, oh, I got 3 H2s. The 3 H2s cancel out. The other side, all I'm left with is 2 CO2s and 3 H2Os. So I've got the right equation. Right? And you just need to take these numbers right here and just add them up. So that would be the negative of a negative 278 kilojoules plus 2 times negative 393.5 kilojoules plus 3 times negative 241.8 kilojoules equals, and haven't done this last period, I'll tell you it equals 1234 kilojoules. That was an easy number to remember. Okay. Man, that's a lot of work, isn't it? We did all that work so we could do this math. But think about it. Every time we go through this process, we're going to do this math. And every reactant, we're going to turn around. And every product, we're going to leave the way it is. And any coefficient, we're going to multiply by that coefficient. No coefficient, so that's a 1. Coefficient, that's a 2. Coefficient, that's a 3. So I really don't have to go through this whole process every time. I can just add up all the products and subtract all the reactants. Because that's the math I did there, right? I added up the products, the CO2 and the H2O, and I subtracted the reactants. Because the reactant I'm always going to turn around. So it's always going to have the opposite sign of what I get off the table. All I have to do is multiply by their coefficients. So add up the products, subtract the reactants. And you'll get that 1, 2, 3, 4. Okay, why does it work? Because we can do all those steps. And all the elements cancel out. That's why it works. All the elements cancel out. Okay? But it works. So it makes problems like this much easier. Oh, my delta heat formation. So I went to a table, looked up some heats of formation, and I want the heat for that reaction. I could go through the process of making C2H6 out of its elements, but then the first thing I'd have to do is turn it around because it's a reactant. I could make CO, I could make the CO, right? But I have to multiply it by 4 because there's 4 of them. I could make the H2O. Ooh, well, this one's gas, that one's liquid. I should probably make that go. Ooh, it says liquid here, got to make sure. I left the number for O2 off because O2 is an element and delta H for that is 0. Right? So we could do this problem exactly the way we did the last one, or we could do it a little bit shorter. Here's the shorter. The delta H for this is the products minus the reactants. So the products are 4CO. So I'm going to take 4 times the 1 for CO, negative 110.5 kilojoules, plus the other product, water. So 6 times that number for water, and the water's the liquid one, so it gets a little bit more energy, 285.8 kilojoules. Minus the reactant, so minus, subtract, 2 times negative 84.7, got that negative there. Minus 5 times 0, because O2 is 0. Okay, I put that minus there to remind you if there's 2 reactants, you want to subtract both of them. Okay? and you push those buttons, 4 times negative 110.5 plus 6 times negative, got my negative there, 285.8 minus 2 times negative 84.7 equals negative 1987 kilojoules. Okay, a lot shorter than doing this, but all of these steps are baked into that math. Got the negative here because I turned the first one around and multiplied it by 2. Right? Got the 4 here because I made 4 of them. If I'm going to make 4 times what it takes to make 1. I made 6 times what it takes to make 1. Subtract, because I have to unmake the C2H6. I'm not making it, I'm unmaking it, I'm tearing it apart. So it's products minus reactants. The most common mistake people make is going the wrong way, because you want to start with the stuff you start with. But no, you got to start with the products, subtract the reactants. So this math and this math are the same, we just don't have to show all the steps. Because it's going to work out every time. I'm always going to make the elements cancel out. So that is how you calculate entropy. So you'll do that, or enthalpy. You'll do that on the homework tonight.